Picture a line of stepping stones. You can land on the same stone again. Which paths get you exactly to 7? Now make it concrete. Our choices are 2, 3, 6, and 7, and we want every combination that totals 7. Here are the answers we want to discover. 2 plus 2 plus 3, and also just 7 by itself. And notice we return the actual combinations, not positions. This problem cares about the numbers we picked. What would you try first? Maybe keep adding numbers until you hit 7, and back up when you go too far. Try the obvious path. Pick 2, then another 2, then maybe 3. That works, so we save that combination. But now what? If we also try 3 then 2 then 2, that is the same combination in a different order. So the pain is not just searching. It is generating the same answer again and again, unless we control the order. And if we keep exploring after the sum passes 7, we already know that branch can never recover. Pause here. We keep discovering facts, then throwing them away. We know the current sum, and we know which earlier choices set the order. So what information do we wish we carried into the next step, so we do not make duplicates? Here is the move. We do backtracking, like walking a maze with a chalk trail, and we carry a start position forward. That start position means, from here, you may reuse this number or move right, but never go back left. Same idea, said another way. We build combinations in non-decreasing order, so each answer gets generated once. You might think we should move to the next position after picking a number. Do not, or you would lose repeats like 2 plus 2 plus 3. So the rule is simple. When we choose a number, recurse from that same position. When we skip it, move right. Start with an empty path, remaining target 7, and start position 0. We begin at candidate 2. Choose 2. The path becomes 2, remaining becomes 5, and we recurse from position 0 so 2 can be used again. Choose 2 again. Now the path is 2.2, remaining is 3, still from position 0. Try 2 one more time. Remaining would become 1. No candidate from here can finish that, so this branch will stop soon. Back up one step. From 2.2, move right to 3. Now remaining becomes 0, so we found 2 con 3. Back at the top, we eventually try 7 directly. Remaining becomes 0 again, so 7 is our second answer. Notice what changed. We still explore possibilities, but the start position prevents reordered duplicates before they even appear. The search can still branch a lot, so the time depends on how many paths we explore. The extra memory is the recursion path and saved answers. Let's write it. First we set up results and path, then define backtrack with start and remaining. Those are the two pieces we tracked in the trace. If remaining hits 0, we save a copy of path and return. A copy matters, because path keeps changing afterward. Then we loop from start onward, choose a value if it fits, recurse from the same index, and pop to undo the choice. Last step, call backtrack from 0 with the full target, then return all the combinations we collected. That is the stepping stone rule. Keep moving forward, and you never count the same path twice.